Hi everyone, thanks for coming today. I'll be presenting our paper called Towards a Generalizable Place Name Recognition System, which is submitted to the Geographic Information Retrieval Workshop. So this is the outline of my presentation. I will start by describing our project and the problem definition, and then continue with the background work related to this paper. And I will focus on the generalizability work previously done. This will be followed by the data sets we have used and the data set we have created, annotated data set, and the related challenges regarding the data set. And then continue with the methods and tools. And finally, we will talk about the results and some future work. So what is our project? Our project is called Emerging Markets Welfare Project, which aims to identify a new welfare regime in emerging market economies. It may sound complicated. It's a social sciences project, and the work package 2 of this project is related to our paper, which is to create a protest event database and use natural language processing and machine learning techniques to do information extraction for multiple languages and for multiple countries, which requires generalization. So the final system of this work package should be able to work for multiple languages and for multiple countries. So the aim is to extract events from a news document. So, but not just events, but also information about the events, such as the location, organization, and people. And for this specific paper that I will be talking about today, we focus only on the place names about events. So given a text document, which is an event sentence, let's say, we would like to know the location information of this event. And this is the tasks related to our events. So it starts with detecting the protest events from news, and then other information related to the protest events. So that was the what part of the paper. This is now I will talk about the why part. Our main objective and motivation in this paper is to analyze the available tools and data sets and to see if we really need in the first place a new system or a new data set. And then we draw attention to the importance of generalizability to create systems that work well in different domains and different languages. So we focus on cross dataset results. We focus on not just the seen and well-known entities, but unseen entities and unseen features of entities, such as like English text from an Indian news. And finally, we would like to brainstorm with the audience on possible ways to creating such systems. So our main contributions can be summarized as follows. We have created several tools for to speed up research in this area. So we have used ACE dataset, which is really complicated and annotated for many different entities. So we have created a converter which is specific to place name recognition, which will hopefully speed up the research. And by using available tools, we have created a word embedding trainer and the lookup table-based models, so both of which can be used in a quick fashion to get results so that research in this area will speed up. And our second main contribution is the creation of a gold standard corpus for place name recognition. This corpus is created actually for event extraction, but in addition to the event, it's also annotated for location, person information. So it's another contribution to this domain. And finally, we have analyzed and extended the available tools, available place name recognizers by merging datasets. So background on this work. Geographic information retrieval means taking a text as an input, mostly as a text as an input, and finding the geographic entities in a text document, not just the detection of the geographic entities, but also information like their physical location or their several other features about those entities. And many of the geographic information retrieval systems use either named entity recognition tools or made up their own rule-based systems. So named entity recognition is a well-known task in natural language processing. Simply, it's creating a system where the input is a text and the output is the proper names like people names, location names, and organization names in that text. And since it's a very well-known task, there are many tools available, and conditional random fields and neural networks dominate these systems. And finally, generalizability is an emerging research area in natural language processing, which I will describe in detail. So our work can be considered in the intersection of these previous works. So some consider generalizability, some consider named entity recognition, as a solved task because especially the neural network-based, deep learning-based systems have a really high, impressive scores. But Augenstein gives a really good analysis of the state-of-the-art named entity recognition systems, and they report that the scores on well-known datasets for well-known entities with well-known features is really impressive, but these systems fail to detect unseen entities from, for example, different domains or from different countries. And they report that the performance scores, the impressive scores, are the result of the known entities inside the test documents. So since the novel entities are expanding, so we always have new names of organizations, new people names, it's impossible to create a single data set that includes all possible named entities. So the data set should be finite, but should be in high quality so that it generalizes better. And secondly, we should have high quality systems that can generalize well by using finite resources. So in addition to the previous work, what we did is that we merged several different data sets, and it brings its own challenges. And we have the previous work on generalizability focus on inset results, but in this work we also analyzed the cross data set performances, and we compared our results with other geographic information retrieval tools. So at this point of the research, we focused on the high quality data sets, but future work also includes, which we started doing, creating our own place recognition system, which will be a neural network based system. So since our test set is Indian news, English news from India, we have a lot of unseen entities and unseen features because the characteristics of English used in Indian news is different from the regular English. So I'll continue with the description of our datasets. First dataset we used is a very well-known dataset for named entity recognition. It's called the Canal 2003 English dataset, which is used during the shared task, named entity recognition shared task. It's taken from the Reuters News, and it's tagged for location, organization, person, and MISC type of entities. MISC contains entities that does not belong to the other three groups. So in order to keep it simple, we named the training set as C-train, validation set C-valid, and test set as C-test. The second data set we have used for training is ACE 2005 data set, and it's also made up of news articles and has the following entity types, which are facility, location, organization, geopolitical entities, and person. So geopolitical entities can be mapped to location because mostly they are country names, but this can be problematic as well, as we will see soon. So this is the gold standard corpus, annotated corpus that we have created. It's English news from India dataset. So it's made up of 116 news articles. And since it has a small size, it's only used for testing the performance of the systems. It's tokenized by the UCTO tool and annotated by two annotators, and the disagreements between the annotators are resolved by a third annotator. So this is a general information about the gold standard corpus we have created. Let's talk about some characteristics of this corpus. So only the event sentences is annotated in these news articles. Since the main aim is to extract events from news, only we have done annotation for the event sentences. So the entities that are not inside the event sentences are left unannotated. There are some capitalization problems only in the news from 2001, where we don't have capitalization for the named entities, for some of the named entities. And this dataset is annotated for the facility type of entities as well, which is not available in the kernel dataset. So we have to either map the entities to organization type or location type, or just remove all the entities. So these are all the problems we have when we try to use different data sets instead of the same data set. The challenges of merging data sets as well. So finally, I want to mention the characteristics of the English used in India. So the unseen features of this data set. There is an ambiguity of common nouns versus proper nouns. So in India, we have words that refer both to common nouns and proper nouns, which cause an ambiguity. Also, there is a problem related with the spelling of the entities. As you can see here, like a person name has many different variations. The one above and the one below is a location name, which has like 6 variations, which are very similar. So for a given location name, it's if the system just memorizes the entity completely, this will be really difficult to detect for the Indian location names. Now I would like to continue with the methods and the tools we have used. So first, what we did is to compare different models and get their relative performances. So we have used conditional random fields-based WAPT tool and neural network-based NeuroNER tool to see which type of model performs better for this task. And we only compare the inset results for each tool. And secondly, what we do is compare this time the data sets. So which tool generalizes better is a question. So we look at the cross this time. We look at the cross dataset performance, and the secondly, we look at the quality of the dataset. So, which dataset is better to train our models so that it generalizes better. So I will describe quickly the tools we have used. First tool is called the Logit tool, which is a frequently used sequence labeling tool, and it has the following labeling models: logistic regression, hidden Markov models, and linear chain conditional random fields. It also has various optimization and regularization methods. So sequence labeling is the labeling of a data which is sequential, like most NLP tasks, such as post tagging, where the input is in a sequential nature. In this type of tasks, context information is really important. So the system that's doing the sequential labeling task must take into account the neighboring words and the context information. So I will briefly talk about the model types that this Logit tool uses. It uses, this is a really nice illustration, I think, of the tools. So we start with a naive Bayesian assumption, and if the input is in sequential nature, if we assume the independence, then it's called the hidden Markov models. And if we conditionally calculate the probability distribution, it will be a linear chain CRF, conditional random fields model. So conditional random fields calculate the conditional probability distribution over label sequences by taking the transition probabilities of the labels into account. So the second tool we have used is called NeuroNER. It's an artificial neural network-based named entity recognition tool. It uses the bidirectional long short-term memory, which is a type of recurrent neural network. So bidirectional LSTM is known to perform very well in most NLP tasks because it is suitable for the sequential, to analyze the sequential data, and it takes into account the context information because of the type of the architecture. And long short-term memory enables taking into account both the global features and also the local features. So on top of this neural architecture, they also have a label sequence optimization layer, which is similar to a CRF-based model. So this is the overall architecture of the tool. It starts with the character and token embeddings, and by using the recurrent neural networks. And their combination is given to by an STM layer, which produces the predictions for each token, label predictions, so the named entity predictions. And finally, by taking into account all the predictions made for each token separately, an optimization label layer finds the optimal sequence of labels by taking into account the predictions. So this is the results of the first experiments we have used. As you can see, there are too many results we have obtained, and actually we have two separate tables here. The table on top means that the programs, the models are trained using the ConLL training data set. And the second line divides this table into three parts, which are the test sets. So you will, so here we see that results that obtained when we train the model, Wapiti model, on ConLL training set and testing it on the ConLL test set. As you can see, we have three test sets. And the table below shows the models results for models trained on the ACE training set and the merged corpus of ACE plus the kernel data set. So this is the most comprehensive training set that we have. By looking at the results, we can see that NeuroNER outperforms in all cases the Wapiti tool. So we also see that when we train a NeuroNER, for example, using the kernel training set and testing it on the kernel test set, the results are really impressive. So it's like the F1 score is 0.92, but if we test the same system on the ACE test set, we see that we have around a 0.3 decrease in the performance. And same phenomenon can be seen in the Wapiti tool as well. So the 0.85 goes down to 0.58. And a similar phenomenon is also visible when we train the model using the ACE training set and testing it on the kernel test set, which refers that the results attained on the inset results can be impressive, but when we test them on the different data set, the performance really drops. So this was to ensure the quality of the tools and data sets. So here are some findings about these results. So both models perform well on known tasks when they're trained on the same domain, which are like frequently used data sets. And the second finding is that neural network-based NeuroNER generalized better, so it had a higher performance when we tested on a different data set. So probably the reason is that using an embedding-based system rather than a feature-based system implicitly learns these features and generalizes better. Another finding is the training time. CRF-based Wapiti took much less time to train, and it didn't generalize as well as the NeuroNER tool probably because of memorization of entities. Since the feature-based systems are binary systems, they either match or don't match. So it's an exact matching. So when the sources are limited, these type of systems may not perform well. So I will continue with the final results that we have obtained on the test set that we have created. So what we did is in the final test set, that as I mentioned before, we have merged the two training sets, ACE and kernel, to generalize the named entities better. But we had some problems about the mappings of the entities because different data sets use different annotation guidelines. So here are the results for the tests we have obtained for the English news from India dataset. We give another contribution that we make is that we give the results for the frequently used geographic information retrieval systems, which are Edinburgh parser and Stanford NER, which is frequently used by GIR systems. We have two baseline models, which are lookup-based models, which use lookup tables, which contain names of place names from India. As you can see, they have really low scores, low F1 scores. So also we see that Edinburgh parser and Stanford NER has around 0.50, 0.56, which are a lot better than the Wapiti tool that we have used. And finally, we see that the NeuroNER tool, which is the version of the NeuroNER tool, which is trained using the merge dataset, outperforms all other models. So even though it's a small improvement over the version which is trained on the kernel training set, we can see here that we obtain a small improvement by merging different data sets. So this suggests that by merging we can generalize better. So our future work includes creating our own place name recognizer, which will be a neural network-based model. We also planning to organize a shared task, which is called the Lab on Protest News, which aims to extract information for multiple languages and countries about protest events. So we also planning to expand the data set for the named entity related annotations, and the annotations is done for the Indian news for now, but this will be expanded to include news articles from these countries as well. So the resulting the program must be able to generalize for all these, for news from all these sources. So I will briefly finally mention the shared task that we will organize next year. It's about extracting information about riots and social events. So we are planning to test and improve the state-of-the-art methods for text classification, information extraction, which does not focus on a single data set, but focus on data from multiple countries, and especially less studied countries like India, China, or Turkey. So here's a summary of our talk. We started with the talk about the generalizability of place name recognition systems, which is an emerging important research area. And the generalizability of name entity recognition systems is a baseline for geographic information retrieval systems, because many of the geographic information retrieval systems use the available NER tools, name entity recognition tools. We have shown that we outperform the baseline GIR systems, but still more improvements are necessary. We have also shown that by merging corpora, we have obtained a slight improvement. So merging corpora is a step towards generalization, but it has its own difficulties. We also seen that neural networks generalized better for this task, and we still need a lot of resources for, especially for less frequently used languages and for countries. And our shared task will be tackling these points. So thank you for listening.